Okay, let's get started. Let me start by taking roll first. Anderson is here. Chesmore, Gonzalez Albo, Hickey, Hislop, Jabbar, Jones, Labrador, McKeon, Miller is here. Peterson is here. Papa, Simpson, and Welter. What's your last name again? Hmm? Oh, okay. Is this it? No? That's this is the only one that I had on my desk upstairs, so I don't know if somebody else removed it from here when you left it. Okay, so Miss Kiki is here. And I think that's it. All right. So we're going to continue our discussion of chapter, the thermodynamics chapter, on which assignment 6 is based on. Okay, so we talked about entropy. Just to remind you of what entropy is, it's basically a measure of degree of disorder of a system. And we talked about the fact that the spontaneity of a process, including chemical reactions, is basically a combination of some sort between entropy and enthalpy. And we finally, see if I can get to that particular slide, established that delta G, this equation here, is basically what we use to make a prediction as to whether or not a system or a process for a system is spontaneous. Simply put, if you plug in the values of delta H, T, and delta S into that equation, then delta G, if it's positive, would indicate that the process is non-spontaneous, and delta G, if negative, would indicate that the process is spontaneous, all right? And I think that's where we left off the last time. So what we're going to look at now is the relationship between delta G and what we've learned earlier as far as chemical equilibrium is concerned. Do this here. All right. So I'm just going to start off with this equation right here. It was shown that the free energy of a reaction is equal to this expression right here. Delta G is equal to delta G under standard conditions plus RT ln Q. And remember, Q is the reaction quotient, which we learned about earlier in this course, which is basically product of the concentration of the products divided by product of the concentration of the reactants. T is the temperature in Kelvin, and R is a molar gas constant expressed as this value right here. So that's basically for any reaction. Now, if the system is at equilibrium, then what happens is that there are two things that will come into play. The delta G value here would be equal to 0, and the Q value, of course, as you should know from before, would be equal to K at equilibrium. So if we put 0 here and K here, this is what the equation becomes. 0 is equal to delta G standard plus RT ln K. And this equation here basically gives you the relationship between the standard free energy and the equilibrium constant. So we can rearrange it to get this equation right here. Delta G standard is equal to minus RT ln K, all right? So basically, we can calculate the standard delta G value for a reaction if you know what the equilibrium constant is for that reaction at a particular temperature. So based on what we have just discussed, we have these two graphs here, this one representing a situation for a spontaneous reaction, where delta G is negative, and this one for a non-spontaneous reaction where delta G is positive. So let's focus on the one on the left first. Delta G is negative, which means that the total free energy of the products will be less than the free energy total of the reactants, right? So that's why we have delta G less than 0, okay? And as you go from reactants to products, this is how the free energy changes. And it gets to a minimum right here, where Q is equal to K. Now, before, Q would be less than K, which makes sense. It would make sense that if Q is less than K, that means the reaction will shift to the right in order to achieve equilibrium. And that's exactly what happens until you get to this minimum point here where Q is equal to K. So at this equilibrium position, you see here that the amount of products or the concentration of products at the equilibrium position will be greater than that of the reactants, right? And that's basically what happens when delta G is negative. In fact, let me write something above here. So remember we said, I just showed you the equation, delta G is equal to minus RT ln K, right? So if delta G is negative, that means that the ln K will be positive, which would mean that K would be very large. And if K is large, that means that the amount of products present at equilibrium will be greater than that of the reactants. And that's exactly what this equilibrium position shows. It's closer to the pure products. So that tells you that the amount of products present or the concentration of the products present would be greater than that of the reactants, right? So that's what happens in the case of delta G being negative. Now, in the case of delta G being positive, you're going to get this curve or this graph, which is essentially the mirror image of this graph right here. So in this particular case, the free energy total of the products would be greater than that of the reactants. So basically, we're talking about a situation where the reaction will be moving in the other direction. So therefore, what will happen is that as the free energy decreases, as the reaction progresses, and it gets to this equilibrium position here, which is obviously closer to the reactants. And therefore, what that indicates is that at the equilibrium position, the concentration of the reactants will be greater than that of the products, all right? So that's what happens in this particular case, all right? So, you know, this graph is a very good diagram to show you, these two graphs, basically showing you the different relationships between Q, K, and delta G. And it's very important that you understand the relationship between these different terms. Okay. Any questions about this? Any questions about what I've just shown you, these graphs? No questions? Okay, so this is just a summary of the mathematical relationship between delta G and K, all right? So we're assuming that RT is constant. Well, R is definitely constant, and T can change, but let's assume that T is standard temperature, which is 25 degrees Celsius. So if that's the case, if K is greater than 1, that means that ln K will be positive. If ln K is positive, because of this negative sign, that means that delta G will be negative, which means that at equilibrium, the products will be favored over the reactants, all right? So that's what happens if the equilibrium constant is greater than 1. If the equilibrium constant is equal to 1, that means that ln K is 0, and that means that delta G is 0. And what that means basically is that at this point, for a reaction, both products and reactants will be equally favored at equilibrium. And then finally, if K is less than 1, that means that ln K would be negative, which means that delta G will be positive, which means that at equilibrium, the reactants will be favored over the products at equilibrium, all right? So again, it's very important that you understand the relationship between K, G, or I should say delta G, and what it actually means in terms of the compositions of the reactants and products at equilibrium, all right? So very important that you understand this and appreciate this. Okay, so based on what we have covered, everybody got a copy of assignment number 6? Number 6? Okay, so based on what we have just covered, you should now be able to do, and somebody told me that we went as far as question number 3. Let me see here. You should be able to do pretty much all questions up to and including question number 6. In fact, pretty much all questions. But let me bring up assignment number 6. Okay, assignments. Let me see here. Oh, okay, thank you. Who said that? Oh, Miss McKeon just said that I apparently didn't. Oh, it's published now, Miss McKeon. I'm downloading it now. Okay, so I'm going to scroll down to question number. So I was told that we have done up to question number 3. All right. So I'm just going to scroll to question number 4 now. So question number 4 says, write a balance equation for the formation of 1 mole of iron 3 oxide from its elements. So let me turn on my writing thingy here. Okay, so the equation, of course, you're going to end up with 1 mole of Fe2O3. So obviously, it would be iron reacting with O2 to form Fe2O3, all right? Which is a solid. Iron is a solid. Oxygen is a gas, right? So basically, we're going to need 2 here. And to make sure that we end up with 3 atoms of oxygen on either side, that would be the equation, right? That's the equation for the formation of 1 mole of iron 3 oxide, all right? So the next question is, what is the free energy of the formation of 1.00 moles of Fe2O3? So the free energy standard of this reaction would be equal to the free energy of formation of Fe2O3 standard minus the free energy formation of Fe, and this would have to be multiplied by 2, so 2 times. And then to that, we're going to add the free energy 3/2 times the free energy of formation of O2 gas. And that would be the equation. Now we can make life easier for us because these 2 are elements. And if you remember, we said that the free energy of elements by themselves, not combined with anything existing in their normal state under standard conditions, will be 0, right? So this will be 0, and this will be 0. So basically what we need to do now is look up the value for the free energy of formation of iron 3 oxide, which is in the tables I talked about last time. So let me see here, tables, where are you? Tables. And free energy or thermodynamic data, download. Okay, so for iron, okay, for iron 3 oxide, the free energy is minus 742. So I'm going to write that here. So for the iron, it's minus 742.2 kilojoules, all right? So let me get back out of this. Okay. And let me get back to this. And okay, so basically, this is what this is equal to. So therefore, this works out to be minus 742.2 kilojoules. And that's the final answer. So that's a free energy for the formation of, well, actually, there's one more step. A minor step, but I'm going to go through it anyway. So this is for every mole of Fe2O3. So basically for 1.00 mole of Fe2O3, the amount of free energy will be minus 742.2 kilojoules for every 1 mole of Fe2O3. And this will equal to minus 742 kilojoules. And I hope the reason why I'm showing you this, even though the answer is pretty much the same, is because you could be given a question where this number is different, right? So therefore, this is how you go about answering that part of the question. Okay, so that's basically how you do 4A. Any questions so far? Any questions? Any questions out there in Zoom? Any questions? Going once, going twice. All right, so let me clear this and do this and scroll down. Okay, so this question is asking, what is the free energy when 454 grams, which is 1 pound, of iron 3 oxide are formed from the elements? So basically, what you're going to do is start off with the 454. Or 54 grams of Fe2O3, and you're going to convert that to moles. So you're going to have 1 mole of Fe2O3, and down here the molar mass. Let me do a quick calculation of that. What's the molar mass of iron? Can somebody tell me what that is? $55.85. Okay, so 55.85 times 3, and then I add to that 3 times 16, which is 48. So according to my calculation, the molar mass of iron 3 oxide is 215.55 grams of Fe2O3. So this goes with that. And then the next step would be the value that we calculated for the free energy for the formation of 1 mole. Can somebody remind me of what that is from the previous part?
You said you multiplied the molar mass of iron by 3?
No, the oxygen by 3.
You said you multiplied by 3 and then the oxygen.
No, I multiply. Let me do it again. It's 55.85, right? Times 2. Oh, okay, I think, okay. Oh, my bad. Okay, yeah, you're right. So this would be 159.97. Thank you for that. Okay, so this unit goes with that. Huh? Oh, 0.7. You know what? Let me do it correctly. It's 159.7.
Yeah.
Thank you. Okay, so this goes with that. And now we're going to, in this conversion factor, use the result that we got from the previous part. What was the answer that we got? Minus 0.2, and this would be kilojoules, right? So this goes with that. So we have to work this out. So that would be 454 times 742.2 negative divided by 159.7. And that, and again, please correct me if I'm wrong, but I got minus 21, round off to 3 sig fig, so 2120 kilojoules. All right. Okay, any questions about that one? Any questions? Any questions? Okay, let me clear this. Do this, scroll down. Okay, now in this case, it says using the value of delta S and delta HF, enthalpy of formation standard, calculate delta G for each of the following. So even though you can actually look up the delta G values and calculate it based on that, that's not what the question is asking for. The question is asking for you to use the values of delta S and delta HF to calculate delta G standard for the following. So what I'm going to do is just basically do the work for one, show you how to do one, and basically you're going to use that same process to do the others. So in this case here, we need to find delta S standard, which would be equal to the entropy standard of lead 2 chloride minus the sum of the entropy standard of lead solid plus chlorine standard entropy of Cl2 gas. All right, so that means we need to go to the same table I talked about earlier. This table right here. And what we're going to look for are the entropy values, which are the values on the third column, starting with lead 2 chloride. So let me see if I can find that. HIJKL. Oh, interesting. Seems as if there's no lead 2 chloride. There's lead 2 bromide, lead 2 sulfate, lead 4 oxide, lead 2 plus. Okay, so what I'm going to do is look up the standard entropy value of TbCl2. And okay, 136.0 is the answer. Oh. So this would be 136.0. 136.0, and the units, of course, would be, what did they say the units were? Hold on. Joule per mole Kelvin. Okay, so this would be, keep up to it. So this would be joules per mole Kelvin. All right. And then we're going to minus from that the sum of the entropy of lead, which is okay, lead. Where's lead? Okay, so lead is 64.81. So (64.81). Again, this would be joule per mole Kelvin plus for chlorine. So now I have to scroll up to find the value for chlorine. And for chlorine, the value is 223.07. (223.07 joule per mole Kelvin). All right. So now that we have that, we can do the number crunching. So what I'm going to do is add what's within the parentheses first. So that's 64.81 plus 223.07. And then I'm going to subtract that from 136.0. And according to, hold on, let me do this again. 64.81 plus 223.07 equals 136.0. Okay, so according to my calculations, this works out to be equal to 151.9 because I have to round off to one decimal place. So 151.9 joules per mole Kelvin. Now that's just the first part. The second part is that we need to find delta HF. Yes, sir. Yeah, negative. Yeah. Standard enthalpy of formation. So we have to go back to the table again and look up the values for, let me set this up, enthalpy. Well, this should be enthalpy of formation of PbCl2, which again, we have to look up online because we don't have it in the tables, plus or minus the sum of enthalpy of formation standard of Pb solid plus that of chlorine. And this is made easier because lead and chlorine are both elements. So therefore, we know that these values will be 0. So basically, all we have to do is look up the enthalpy of formation of PbCl2. So let me do that. So this time we'll be looking for the standard enthalpy value of lead 2 chloride. Let's see what we have here. So according to the information here, that value is minus 359.41. So basically, we're going to put that here. Here. So that would be minus 359.41 kilojoules per mole. Yeah, I'm about to do that. This thing keep coming in. Well, let me do this. Okay. So minus 359.41. There should be a 4 here. So this should be a 4 here. All right. So the answer will be minus 359.41 kilojoules per mole. So now that we have those two values, we can plug it into the delta G equation. Now remember, delta G standard is equal to delta H standard minus T delta S standard, right? We have found delta H, we have found delta S. T would be standard temperature since we have the symbol would indicate that these are standard values. So therefore, and T would be equal to 298 Kelvin, which is the standard temperature, which is the same thing as 25 degrees Celsius. So all we have to do now is to plug these numbers into this equation. Starting off with the delta H, which is, so delta G standard will be equal to delta H, which is minus 359.41 kilojoules per mole, minus T, which is 298 Kelvin, multiplied by the delta S, which is minus 151.9 joules per mole Kelvin. But you'll notice that in order to make everything consistent in terms of units, since the kelvins will cancel out here and here, you're going to end up with joules per mole here, but we have kilojoules here. So what I'm going to do is convert the joules to kilojoules. So you're going to have 1 kilojoule over 1,000 joules. And that is what we need to work out to get the final answer. So it's 151.9 divided by 1,000. And then I'm going to put a minus sign in front of that and multiply by 298. And then I'm going to subtract that from minus 359.1. Okay, I keep messing up here. Let me do this again. So And then, okay, so according to my calculations, and again, please check to make sure I'm doing the right thing, but this is what I got. I got minus 314, 0.14. And this would be kilojoules per mole. All right, so that's basically how that is done. And basically it's the same process for, all right? Basically it's the same process for the other parts of that question. All right? Okay, any questions about this? Any questions? Okay, so is it okay for me to clear this? Can I clear this? All right. All right, let me scroll down further. So basically you can do B, C, the same way we have done A. Okay, now this question says that methyl alcohol has the enthalpy, not enthalpy, free energy of formation equals to that, and it gives you the equation. And it says calculate Kc for this reaction at 25 degrees. Now remember, the relationship between Kc and the standard enthalpy of formation is delta G standard is equal to minus RT L and K. So if that is true, then what is K equal to? What's the expression for K? Let's see if you can figure it out based on your previous algebra experience. If delta G standard is equal to minus RT ln K, then what would K be equal to? Let's do this stepwise. What would ln K be equal to? Based on this here. Okay, so minus delta G over RT. Very good. So if this is true, then what is K equal to? I'm sorry? What do you call that? Inverse of the natural log. E, exactly. Raised to the minus delta G over RT, all right? So basically, they gave us delta G, right? They gave us T, and we know what R is. R is equal to 8.31 joules per mole Kelvin. So we have all that we need in order to answer this question. So that's e to the minus delta G. So that's minus 166.27 kilojoules per mole divided by R, which is 8.31 joules per mole Kelvin, times T, which is 25 degrees Celsius, which is 298 Kelvin, all right? Now, again, we have to do some unit conversion here because we have joules here. Well, firstly, the moles will cancel out, the Kelvin will cancel out, but here we have kilojoules and here we have joules, right? So I'm going to add another conversion factor here where we convert from joules to kilojoules. We're going to put 1,000 joules down here, 1 kilojoule above, so that this joule unit will go with that joule unit, this kilojoule unit go with that kilojoule unit, and then we have to just simply work out the rest of it, all right? So this is what we need to work out. So what I'm going to do is I'm going to take the 166.27 negative. I'm going to divide that by 8.31 times 298. And then I'm going to multiply by 1,000. And this negative will cancel out that negative. So based on my calculation, I got e to the 67. So let's see what that gives. Okay, where's that key? Okay. Okay, so according to my calculation, this works out to be 1 point 1.3 times 10 to the 29. That's the answer I got. Again, please check to make sure I'm doing the right thing. So I got 1.3 times 10 to the 29. And this answer makes sense because if delta G is negative, as we saw earlier, that means that ln(k) would be greater than 1, which means that K would be definitely large, which is what we definitely observe here, all right? K is a large number. And basically what that means is that the reaction favors, or the equilibrium position favors the products. Okay, any questions about this one? Any questions? Any questions? Any questions? Okay, do I need to, can I clear this? Okay, scrolling down. Okay, now this one, it says consider the formation of NO from its elements, and it gives you the equation. Use the free energy data provided to calculate Kp. So what I would do is I would find, or I would look up the delta G values for each of these, right? So we don't need to look up for nitrogen and oxygen because, again, those will be 0. So what I'm going to do is look up the value for nitrogen monoxide. Hopefully it's here. Okay, here it is. So the free energy formation of nitrogen monoxide is 86.55 kilojoules per mole. So shucks. Okay, so basically, this is 86.55 kilojoules per mole. That's the delta G value. So therefore, delta G for this reaction, standard, would be equal to 2 times 86.55 kilojoules per mole minus 0 plus 0. So let's see what that gives. 86.55 times 2. So that would be 173.1 kilojoules per mole. All right. Now, again, relationship between delta G and Kp is this. So basically, it's the same equation that we're going to use. K would be equal to minus delta G over RT, because the question is asking for you to find K. This time it's Kp, same K, equilibrium constant. So K would be equal to minus 173 point, I'm sorry, e to the minus. Can't forget that. Okay. So K would be equal to e to the minus 173.1 kilojoules per mole, divided by R, which is 8.31 joules per mole Kelvin, times T, which is, again, 298 Kelvin. And again, we have to convert from joules to kilojoules. So 1,000 joules here, 1 kilojoules above. And basically, we do the same thing to get the K value, which I'll leave you guys to work it out, all right? It's the same as in the previous question, all right? So that's basically number 7. Any questions about this? Any questions? Okay, so may I clear this? All right. And let's see. Okay, now this question says, and I'm not going to go through it exactly. I'm just going to give you some guidance. It says, assume that delta H reaction and delta S reaction are nearly constant with the temperature. Calculate delta G reaction at 700 degrees Celsius. Estimate Kp from the new value of delta G. Okay, so basically what you're going to do is, based on the delta G, let me see here. Based on the enthalpy of reactions that you'd have to calculate based on the equation, you're to find delta G, right? So the equation you're going to use in this case is, whoops, not that. The equation that you're going to use in this case is what we met before, which is delta G standard is equal to delta H standard minus T delta S standard, right? Now, in this case, what you're going to do is you're going to find the initial delta H and delta S, basically using the same process that we used before. You look up the delta H values for the reactants and products, find a difference, that will give you delta H, and you do the same thing for delta S, right? And then what you're going to do is find delta G using those same values, but this time the temperature is going to be 700 degrees Celsius, which you have to convert to Kelvin. So you add 273 to that, which gives you 973 Kelvin. So basically, you're going to find a new delta G value where the delta H and delta S are the same, but this time the temperature would not be 25 degrees or 298. It's going to be 973 Kelvin. And you're going to find that delta G value. And then based on that delta G value, you're going to estimate the new value of Kp, which is, again, e to the minus delta G divided by RT, right? So once you find a new delta G value, you plug that into this equation right here and find a new value of K. And that's it, all right? So you can try that on your own. If you have any questions, again, feel free to contact me and I'll help you with that, all right? Okay, so that's basically it for this assignment. I think there's one more thing I need to cover in the oh, can I clear this? Okay, there's one more thing I need to talk about in the PowerPoint. Let me go to the PowerPoint here. Oops. And then that will be the end of this chapter. Okay, so again, very often you'll find a lot of biological applications of, you know, whatever we have learned in chemistry, chemical principles, right? After all, most biological processes are chemical processes. And this whole idea of thermodynamics and free energy and entropy and all that certainly applies as well. So what you're looking at here is something that you may have seen in your biology courses, right? To basically convert from glucose to the products of respiration, which would be carbon dioxide and water, energy would be required. And that energy, energy would be given off, my mistake, right? That's an exothermic reaction, okay? So basically, in order for cells to use up this energy, for example, energy required to build up proteins from amino acids, the energy would first have to come from the oxidation of glucose, right, to form carbon dioxide and water, right? Now, an intermediary which is involved in this process is a molecule I'm quite sure you have met in biology, known as ADP, right? What happens is that ADP will pick up a phosphate group to form a molecule which is ATP. That process requires energy, and that energy comes from the conversion of glucose to carbon dioxide and water, right? In turn, that ATP will release its energy, which allows for this reaction to take place, the amino acids to be converted to proteins, because that would require energy. In so doing, it basically converts back to ADP, right? Now, if you look at the thermodynamics of these reactions, in order for, let's say we're going to choose two amino acids. One is alanine, the other one is glycine. When they react, they form alanyl glycine. And you'll notice here that the free energy for that is plus 29 kilojoules, right? What that tells you is that that process is non-spontaneous, right? Will not occur by itself, okay? So how does it happen? Well, basically, as a result of this spontaneous process, which provides energy to convert ADP to ATP, that process results in ATP releasing energy to drive that non-spontaneous process. So if you look at the chemistry of it, if you add to this equation the process of converting ATP back to ADP, which is an they call it an exogenic process when it comes to free energy being negative. When you do the calculation for the free energy for that change, you see that it's negative, right? So therefore, basically what you're having is a spontaneous process, which is this right here, through an intermediary, driving a non-spontaneous process, which involves the synthesis of proteins, all right? So this is just one of several examples of all the principles that we have learned in this chapter with respect to thermodynamics, entropy, and so on, free energy, applies to biological systems. Okay, so that's basically it for this chapter. What time is it? Okay, we have 30 minutes left. So what I'm going to do now, so let me just say this. So basically, you should be able to be done with this chapter by the time we get back from the break. And I'm going to, this evening, for sure, I'm going to send you back assignment number 4. I'll be grading assignment number 5, and also the do-over test. I keep forgetting to send that back to you guys. So this evening, when I have some time, I'm going to scan and send you back those particular work that you have done. And I would say by this weekend, I'm going to be completing the grading of assignment number assignment number 4 will be scanned and sent back to you. Assignment number 5, I'm going to grade it. Definitely by this weekend, you should receive it, all right? I'm trying to catch up with all my backlog of stuff to grade. So let me just say that if you have not turned in either assignment 4 or 5, please do so ASAP so that I can have that sent back to you so that you can get ready for your next test. Okay, so let me get to the next chapter, which deals with electrochemistry, which, as you're going to see, is a direct offshoot of what we just learned in thermodynamics. So electrochemistry is here. Let me publish it now. That's the PowerPoint. Electrochemistry. Now, as the name suggests, this is where we look at the intersection between chemical reactions and electricity. And basically, we'll be dealing with what we call electrochemical processes. And you'll notice that there's a term that is basically directly related to electrochemical processes, redox reactions. I'm quite sure you'd have met this before in your general chemistry 1. I'm quite sure Erin Miller can get up in front of us and talk to us about everything she knows about redox reactions, right, Erin? She's looking at me like I'm crazy. Okay. So basically, there are 2 types of electrochemical processes, right? You have one type where you have the reaction taking place spontaneously, and that generates an electric current, right? And then you have another case or another type of electrochemical process where you use an electric current to drive a non-spontaneous process, right? Or a non-spontaneous reaction. So those are 2 types of electrochemical processes that we'll be looking at in this particular chapter, all right? So as I said before, we'll be looking at redox reactions, right? And just to give you a quick refresher, this is a simple example of a redox reaction. Basically, redox stands for reduction oxidation, and reduction is basically what takes place when the oxidation number decreases. Oxidation is what takes place when the oxidation number increases, right? And I don't know about you guys, but in my class, when I teach General Chemistry 1, I use or I introduce to my students this sort of memory guide, oil rig, to help you to remember what oxidation and reduction are. Oxidation, this stands for oxidation involves loss of electrons, reduction involves gain of electrons, right? So maybe that will help you in terms of remembering what is what, all right? So in this particular simple example, we have magnesium, right, being converted by reaction with oxygen to form magnesium oxide, right? And as a result of this reaction, what happens is that the magnesium loses electrons to form the magnesium ions, and the oxygen gains the 2 electrons lost, or I should say the 4 electrons total, lost by the magnesium to form the 2 oxide ions, all right? And that's basically what happens in every single redox reactions. Something is losing electrons, which means something else is gaining electrons. You cannot have reduction without oxidation. That's simply just basically what happens in all redox reactions. And another thing I need to point out too is that the number of electrons lost in the oxidation must be equal to the number of electrons gained in the reduction. Always happens, without any exception, all right? So that's what happens in redox reactions. So we call these 2 half reactions, right? This is the oxidation half reaction. This is the reduction half reaction, all right? Okay, so let me just jump to the next slide. So we need to remember, we're gonna go down memory lane. We need to remember how to determine the oxidation numbers, because basically, once you can track the oxidation numbers and their changes, basically you can tell what is being oxidized and what is being reduced, right? So the oxidation number, and if you look in different textbooks, you'll see different definitions. I personally prefer this definition right here. It is the charge the atom would have in a molecule or an ion of compounds if the electrons were completely transferred, all right? So basically, we'll be looking at the different rules for determining the oxidation numbers of different atoms in different substances, right? The first rule is probably the easiest rule. Any free element, elements that are not combined with anything, will automatically be assigned an oxidation number of 0, right? So if you have oxygen, nitrogen, sodium, cadmium, any element by itself, the oxidation number is automatically assumed to be 0. So these are just some other examples. And it doesn't matter if it's a diatomic or polyatomic, if it's a molecule or a neutral species, basically it's 0 for its oxidation number. In monatomic ions, this is the second rule. In monatomic ions, the oxidation number is equal to the charge on the ion, all right? So any monatomic ions, such as these right here, right? The lithium ion has a +1 charge, so the oxidation number is +1. In the case of iron 3, the oxidation number is +3. In the case of the oxide ion, the oxidation number is -2, right? So that's basically the rule for any monatomic ion. The oxidation number on those ions would be the same as the charge. Now, in this case here, this deals with oxygen. And in the case of oxygen specifically, its oxidation number is usually -2, with certain exceptions. And the exceptions would be in the case of the molecule hydrogen peroxide and any compound which contains the peroxide ion. In those instances, the oxidation number of oxygen is -1, all right? So again, oxygen usually has an oxidation number of -2, excepting in the case of hydrogen peroxide and in the case of any compound that contains the peroxide ions. And in those instances, the oxidation number of oxygen is -1. And then the next rule has to do specifically with hydrogen. The oxidation number is usually +1 for hydrogen, excepting if the hydrogen is directly bonded to a metal. In those instances, the oxidation number is -1, all right? Do I have some examples here? No, I don't. Okay, so for example, in the case of, let's say, water, the oxidation number of hydrogen is +1. But in the case of sodium hydride, the oxidation of hydrogen is -1, all right? Because in the case of sodium hydride, we have the hydrogen bonded to a metal, all right? So that's another rule that you need to be aware of. Okay, rule number 5 says group 1A metals, their oxidation number would be +1, group 2A metals +2, and fluorine is always -1. I should add a little statement here, in their compounds. So make a note of that, please, in their compounds. So what I'm saying here is that any compound which contains group 1A metals, their oxidation numbers is +1. Any compound that contains group 2A metals, their oxidation number is +2. And any compound that contains fluorine, its oxidation number is -1, all right? So that's another rule that you need to keep in mind. What's the next one? Rule number 6. Okay, so rule number 6 is very helpful because you can use rule number 6 to help you to determine the oxidation number of all other elements that cannot be determined by the previous rules. Basically, what this rule says is that the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or ion. And I think I have an example of this lined up. So let's say you're given the bicarbonate ion, HCO3, right? And you're asked to write down or determine all the oxidation numbers of all the elements in this particular compound. Well, based on the previous rules, we know that the oxidation number of hydrogen is +1, and the oxidation number of oxygen is -2, right? We know that based on the previous rule. None of the rules before can directly tell us what the oxidation number of carbon is. So I'm going to call that X, right? So let's see how we determine that. Well, based on rule number 6, it says that if you sum all the oxidation numbers of all the elements in the formula, that will be equal to the total charge carried by the formula, right? So as we said before, oxygen is -2, hydrogen is +1. So you set up your mathematical relationship, 3 times -2, because you have 3 oxygens, +1 for the hydrogen, plus the unknown, which is for the carbon. The sum of all those would be equal to the charge, which is -1, right? And all we have to do is solve for the unknown. And when you do that, we see that the oxidation number for the unknown, which is carbon, the number for carbon is +4, all right? So that's basically how you can use these rules to determine the oxidation number of pretty much any element that may exist by itself or in a compound, all right? Any questions about this? This should be basically a review, right? Because this is what was covered previously in general chemistry, if I remember correctly, in chapter 4, maybe, in this textbook that we use, all right? Okay, so any questions about any of these rules? Any questions? All right, so now we're going to get to, again, another thing that you should have covered in General Chemistry 1, balancing redox equations, all right? And it's a step-by-step process, as you should have learned before. So the best way to get into it is to use an example. So let's say you're given this question. You have to write down a balance equation for the oxidation of Fe2 plus to Fe3 plus by the dichromate ion in acid solution. And to be fair to you guys, this is not enough information. I'm just going to say that Cr3 plus is a product as well. So make a note of that, all right? So basically, let's say you're given this statement. You're oxidizing Fe2 plus to Fe3 plus using dichromate, and the chromium-3 ion would be a byproduct as well, all right? So the first thing you do is write the unbalanced equation for the reaction in ionic form, and that would be the equation right there, right? Totally unbalanced. All you did was write down the reactants on the left side and the products on the right side and your arrow in between, all right? The next step is that you separate this equation into 2 half equations, right? So one half equation will represent the oxidation part, half equation, which is going from Fe2 plus to Fe3 plus, and the other equation would be the reduction, going from the dichromate to the chromium-3 plus ion, all right? Then the next step is that you're going to balance all atoms excepting oxygen and hydrogen in the traditional way that we're accustomed to, right? Which means basically making changes to coefficients where necessary. So in the case of the first half equation, there are no changes needed because you have 1 and 1 here for the coefficients of iron on either side. But in this case here, you have 1 chromium ion here, and you have 2 chromiums here. So that means we need to put a 2 here, and we end up with that as a result, right? So that's the second step, or I should say the third step. We basically balance oxygen and hydrogen. Well, we balance other atoms than hydrogen and oxygen in each half reaction. The fourth step is where we start balancing the oxygens and the hydrogens. And the way we do this is that firstly, we balance the oxygens by adding water to the side that is deficient of oxygen. And we add enough water until we get the balanced equation, right? So in this particular case, before we added the water, we had 7 oxygens here, which means that we need to add 7 water molecules. So we have 7 oxygens on the right side, right? So the oxygens are now balanced. Then we have to balance the hydrogens. How do we do that? Well, we have 14 hydrogens here on the right side. We have none on the left. So what we need to do is add hydrogen ions, 14 hydrogen ions on the left side in order to balance the hydrogens, all right? In the case of the other half reaction, we didn't need to do anything because there are no hydrogens or oxygens going from Fe2 plus to Fe3 plus, right? There are no oxygens or hydrogens, so we don't need to balance it. But as you're going to see in other examples we're going to look at, you may need to balance the oxygens and hydrogens in those instances. And then we get to step 5, and this is where most students screw up, all right? Because in step 5, what we need to do is make sure that the total charges are balanced on both sides for each half equation. And the way we do that is that we add electrons to the side with the net higher charge, right? So you look on both sides, you look at the side that has a higher net charge, and you add electrons to that side, and you add enough electrons to that side until the charges are balanced on both sides. So what does that mean? For the first half equation, you have a +2 here. So this was +2. This is +3 total. So that means we add 1 electron to the side with the +3. That will give you 3 minus 1, which would be equal to +2, which balances with the +2 on the left side, all right? So that's how you do for that half reaction. For the next half reaction, let me erase this here. Oops, sorry. Let me, okay, so for the next half reaction, right? Let me just show you from here. You have 14 plus charges, -2 on the left side. So that gives you a total of +12. On this side, you have +6. So that means you're going to add to this side because this side has a higher net charge. The question now becomes, how many electrons do you add to that side? And the answer is that you add 6 electrons. By adding 6 electrons, you're adding 6 negative charges to that side. So that gives you a total of +6 on the left side, which balances with the +6 on the right side. So that's why we add 6 electrons here, and we have 1 electron here. So after doing that, then we have to make sure that the number of electrons here that is lost in oxidation will be equal to the number of electrons gained here in the case of reduction. Because if you remember what we said earlier, the total number of electrons lost must be the same as the total number of electrons gained, right? So the question now becomes, how do we achieve that? And in this particular case, we need to multiply this equation by 6, right? So that we have 6 electrons here, which would be equal to the 6 electrons here. But of course, that 6 multiplying this would also have to be applied to the iron 3 plus and the Fe2 plus, right? So that is basically what we end up with right there, all right? So once we do that, then we add both equations together, and I'm running out of room here. So let me do this. Okay, so you see down here, we have this equation right here. We have this equation right here. We have 6 electrons lost and gained from each equation. So the next step is we add both half reactions, right? And write down what is left after we cancel out the common items on both sides. So in this case here, that would only be the 6 electrons. Let me go back to full screen. So that would be the 6 electrons being canceled out between these two half equations, and whatever is left behind will be the final answer. And as I always tell my students, what I would strongly suggest you do is do a quick final check through to make sure that everything is balanced, all the atoms and all the charges, right? So if we do that, you see that you have 14 hydrogens here, 7 times 2, 14, so that's balanced. We have 2 chromiums here, 2 chromiums here, so that's balanced. We have 7 oxygens here, 7 oxygens here, that's balanced. We have 6 irons, and then as far as the charges are concerned, we have 14 plus charges, minus 2, that's 12, and then 12 plus 12, so that's 24 on the left side. And here we have 6 times 3, 18, 18 plus 2 times 3, 6, 18 and 6, 24. So the charges are balanced as well, right? And therefore you can be very certain that your equation is balanced, all right? Okay, any questions about this? Any questions? No questions? Good, so let's look at, I don't think we have we don't have time for more than one example, so let me just bring this up. Okay. Let's say you're given NO3 minus plus, I'm trying to think of a good one, Mn2 plus to give MnO4 minus plus N2. Let's say you're given that, right? What's the first step? Quickly. Okay, so what would be the half reactions? NO3 minus N2. Okay, 2. Very good. What's the next step? Balance all atoms excepting oxygen and hydrogen. So in this case, what does that mean? Okay, and what about this one? No change because it's already balanced, right? Very good. Next step. Oh, I was about to say 6 H2O to this side right here. What about the second half equation? So 4 H2O would be added to that side. Okay, next step. 12 hydrogen ions. Remember, it's hydrogen ions, right? What about the second half equation? 8 hydrogen ions. Very good. What next? Okay, how do we go about balancing charges? Here, right? Okay. What about the second half equation? 5 electrons to the right side. Okay. Then what? Okay, so we have to multiply. And why do you do that? Whoops. Why would you multiply this by 2? Exactly, because by multiplying this by 2, you're going to get 10 electrons, which basically cancels out the 10 electrons here. So if we multiply this entire equation by 2, you're going to end up with 8 H2O plus 2 Mn2 plus to give 2 MnO4 minus plus 16 H plus 10 electrons. Let me just cross this out just to avoid confusion, all right? And then we do what? Okay, so obviously the electrons will cancel out. What else will cancel out? Okay, so these 12 will cancel out 12 of these, leaving behind 4. What else? Okay, so these 6 will cancel out 6 of these, leaving behind 2, right? And then we write down what's left, which should be the final answer. 2NO3 minus plus 2H2O plus 2Mn2 plus. And then on the right side, we're going to have N2 plus 2MnO4 minus plus 4H plus. And that should be the answer. But of course, as I said before, we do a final check through to make sure everything is balanced. So let's do that now. 2 nitrogens, 2 nitrogens. 6 plus 2, 8 oxygens. 2 times 4, 8 oxygens. 4 hydrogens, 4 hydrogens. 2 manganese, 2 manganese. And then as far as the charges are concerned, we have 2 times plus 2. So that's plus 4. And here we have minus 2. Hold on, something is wrong here. Oh, hold on. What did I say? Plus 4, minus 2. So that's plus 2. And here we have minus 2 plus 4 equals to minus 2, right? So basically, we're going to have minus 2 total charges on both sides, all right? And that's it. And in the next assignment, you're going to get a couple of these. But there's one more thing I need to talk about with respect to this. So I'm going to hold off until next class since it's now 9:12, all right? All right, so I'll see you guys when you get back from the break. Whatever you do, don't do it in excess over the break. Don't burn all your brain cells and all that. Still need it for the rest of the semester. Well, this is the only one that I had in my office. I thought that was yours. So maybe somebody else or another faculty member picked it up. Sometimes they will leave stuff with the administrator. When you enter the doors going into the faculty office region, there's a lady, Kim Regal. She's the administrator. So you may